Hello, and welcome back to another episode of the Hidden Quantum Champions. Today, we are looking into a company that is using tiny macroscopic or nanoscopic carbon nano onions to build qubits. So this is a completely new technology in this series, one of the qubit technologies that I've not been presenting earlier. So definitely an exciting new route to go down and a couple of things to discover here. If you want to learn more about that, about the company behind this, and how they're actually doing it, what their technology is actually about, then stay tuned for today's video as we are diving deeper into Archer. Archer is the company that is using carbon nano onions to build qubits that might even work at room temperature. So here we are, as per usual, on their website. It says Archer up here, and building quantum technologies that drive transformational solutions to complex global challenges. Archer is a quantum technologies company developing solutions for next-generation computing, advanced sensing, and breakthrough medical applications. Our core technologies, and of course the one that I've been talking about mainly, is here on the left side, so breaking barriers with quantum innovation, powering the future of computing, sensing, and biomedical technology. And the 12CQ chip, so we are developing our 12CQ chip to enable more practical quantum computing technology and advanced sensing. And then there's the biochip here. That is also an interesting product that they have. So we are developing a highly sensitive biochip to enable advanced medical diagnostics, including rapid potassium level blood testing. What else is there to learn? So solving what today's tech can't with quantum innovation. Our quantum solution addresses challenges today's technology can't, unblocking breakthroughs in quantum computing, sensing, and healthcare. And then we see here, there's the ASX code, last price, volume, daily high low, and the market capitalization of the company. So that's, I guess, the ticker code here. And you can also review the annual report and the announcements of the company as well. So from that, I assume this is already a stock listed company. They might have done an IPO already at a market capitalization of, so the total number of shares or the value of those shares that is on the market is these 102 million US dollars. This is not financial advice, right? It's just me reviewing the company and being interested in the technology. You decide however you invest your money, in which companies and which not. Down here, as per usual, you find the Stay Connected, a way to get subscribed into their newsletter, and then more about the technology, the company, and recent news. The company is based out of Australia. We see it here. It has 2 offices, one in Sydney and one in Adelaide. Good. Now, let's quickly take a look at the technology, because I guess that's what we are interested in and that's what we want to learn more about. So, our core technologies: advancing what's possible, quantum technologies transforming computing, sensing, and healthcare. Now, of course, because it's very interesting, let's quickly check out the 12CQ chip. So Archer is redefining quantum hardware with its breakthrough carbon-based 12CQ chip. Our scalable, cost-efficient technology powers quantum devices beyond conventional limits. From advanced computing to medical diagnostics and navigation, we are driving real-world impact. Carbon-based quantum hardware, the 12CQ advantage. Our 12CQ chip opens a new pathway to scalable quantum devices that are smaller, more cost-efficient, and operable at higher temperatures than most contemporary quantum processors and sensors. From quantum sensors to qubit processors, so powered by the 12CQ platform, we are building a pipeline that starts with advanced quantum sensors and progresses to scalable qubits and processors. Our first carbon-based qubit demonstrator is on track for 2026. I'm recording this in 2026, a pivotal milestone in Archer's quantum computing roadmap. Built for industry, manufacturable by design, so every step of our development is guided by manufacturability, ensuring innovations can move from lab to industry at scale. We prioritize engineering choices that enable reliable production, integration, and development across real-world application and real-world environments. Real-world impact, magnetometry, diagnostics and navigation. So ARCA's technology extends beyond next generation quantum computing to fields depending precision and reliability, from highly sensitive magnetometry for industrial and biological applications to our biochip for next generation medical diagnostics and navigation systems for GPS denied environments, positioning ARCA at the forefront of the quantum revolution. Okay, so that's everything that we find here for now. Let's quickly talk about what we can learn, right? So first of all, what is this 12CQ about? So 12C, if you're looking into your period table, into the nuclear, like the atomic table with all the different atoms in it, you will find that carbon is at the 12th position. So it means it has 12 protons sitting in its nucleus, and there are 12 electrons, because it has to be neutral, right, circulating in these electron distributions around the nucleus, which is actually pretty good, because it means also that, of course, depends on the number of neutrons that you also have inside your nucleus. If the number of neutrons is balanced, and actually the let's say most statistically likely distribution, or the number of neutrons is not necessarily fixed inside the nucleus. That's why we usually talk about different isotopes. So think about hydrogen as an example. Hydrogen usually has one proton and one electron, but you can also have different numbers of neutrons sitting in your nucleus as well. So you can have the deuterium, which has two of them sitting in there. So usually you have one, that's the most likely hydrogen isotope. So that's the normal the normal hydrogen, where you have one proton and one neutron. Now there's the deuterium, which has two neutrons sitting in the nucleus. And there's the tritium, which has three neutrons sitting in the nucleus. And already for the tritium, it starts to become radioactive. So there's a radioactive decay process. So it's a non-stable isotope of this specific atom called hydrogen. The same exists for every other atom in the nuclear table or in the periodic systems. Some of them have very, very short lifetimes. So they might only exist theoretically or in some decay processes, but you will never find them in nature because they have a very, very short lifetime. And other ones, they might have very, very long lifetimes, but they still decay. And other ones, they are very stable. So you don't find them to decay. Practically, they have a very long lifetime. That is something that is being understood pretty well. And for example, in the case of carbon, you have a pre-relevant carbon isotope that is very well balanced. So the number of neutrons and the number of protons is basically in parity, or you have, let's say, at least a case where you have what is it called? Not an odd, but an even number of particles sitting in your nucleus, so that from the outside you don't have any net spin. What do I mean by that? So spin is a magnetic property that those quantum particles have, a magnetic property that can either point in one direction or into the other direction. If you have an even number, they will usually just counteract. And if you have an odd number, you will have a net spin up or a net spin down, which is a disadvantage if you try to use the spin as a qubit, because now in these onions that I was talking about before that are being used here, you are working with this carbon-12 isotope, so with an isotope or with the carbon atom and an isotope that doesn't have any additional spin momentum, which is very good because now you can induce an additional electron, for example. You can put this into this onion, and thereby you get an isolated spin that you can then manipulate and that you can use to store and manipulate quantum information, which is what we need for quantum computing. So, quick step back. I was talking about onions a couple of times now. What do I mean by that? So, These onions, they're actually nanoparticles that can be manufactured with different processes. I will not talk about the details of those. So there's like chemical vapor deposition, there's oven techniques that you can use. But essentially what you do is you apply a certain set of settings and then you create from carbon, from graphite, from nanodiamonds, whatever you want to call it. You create those objects that under the microscope, they look like little onions. So basically you have carbon atoms that are forming, like for example graphene, which is a 1D layer, a two-dimensional layer, right? So you have these hexagonal settings or the hexagonal distributions of carbon atoms that are forming this perfectly flat sheet, which we call graphene. It's a two-dimensional object because you only have basically the atoms sitting in a plane, and it's the first truly two-dimensional material that has been discovered in nature. Now, you could, for example, wrap this up, right? You could roll this up and then you end up with a so-called carbon nanotube. So then you basically, you take it, you roll it around and until the both ends meet each other and you end up with a tube. But you could also kind of wrap it together and shape it into a sphere, or you grow it as a sphere, and then you would have a carbon ball or a carbon sphere. And now for these onions, you have multiple of these that are wrapped around each other. So you have a small one in the center, a bigger one that is sitting around that, and a bigger one that is sitting around that. You can find nice electron micrographs also on Google if you search for these carbon nano onions. Now, these ones, as far as I understand, and I mean, we didn't see anything about that yet now in the text that we were looking at, but as far as I understand, according to my research, these objects, they are at the core of the technology that Archer is proposing. So they are taking these little nano objects, these spheres, and they are manipulating them. They're controlling them to be in positions, specific positions on a chip. And with that, they can build these nano architectures, these chips. And the idea is now that you put a single spin onto one of those spheres. So you put one additional electron, you charge it with one additional electron. And by that, you basically create an object that behaves, let's say, on a larger scope, like a single electron spin. And the electron is confined on this sphere. Now you can basically point spin up and say, this is my qubit position 1, or spin down, this is my qubit position 0. Now what is interesting about that is that the charging energy of these onions, of these nanospheres, is very, very high. What does that mean? You need a lot of energy to either add an additional electron or to take one off from the sphere. And that's very good because it means that you cannot easily have thermal fluctuations. So when you have elevated temperatures, everything is kind of shaky and moving. And that's why, for example, for most of the quantum systems, you have to cool them down to almost absolute zero temperature because otherwise you have electrons jumping in and out of your qubits and that destroys the whole calculation. So you have to cool everything down so that the electrons don't have enough thermal, randomly statistically distributed energy anymore to hop onto your qubit and to destroy your quantum state. Now, with the carbon ones, the difference is, okay, the energy barriers are much higher now, and that's why it is much more difficult to actually have temperature fluctuations, or for temperature to create those fluctuations, or vice versa. For the architecture, that means you can build something that can operate at higher temperatures, potentially even room temperature. That's, I guess, not figured out yet, but potentially higher temperatures because of this effect that they are using here, this charging effect. Now, of course, there are also certain caveats, and I've also tried to explain that to you in earlier videos. It's not only about being able to have, let's say, specific benchmarks like this charging temperature, but it's always about multiple different things that come together that make a great platform for quantum computing. And I think here in this case, this is something that is actively being researched right now. So what do I mean by that? One thing is the coherence time. So coherence time means if I create my qubit in a specific state, let's say 1, so spin up, how long can I leave this untouched without doing anything to it until it falls back down to 0 or until it kind of creates some randomness to it? So how long does it stay in this initialized position? And there are ways to measure that, and stay in the initialized position also means like what is the point until it basically ends up in some random orientation, right? But this is something called the coherence time, and oftentimes the coherence time is something that goes down as the temperature goes up. Here in this case, because of the lucky material choice and of the high charging energy, I think there is certain advantage. The coherence time, according to my research, is somewhere in the hundreds of nanoseconds, at least for the T1 coherence times. So that means you still have a bit of room to operate, because these qubits, they're driven by microwave signals, and microwave signals, they're usually operating in the single nanosecond regime. So you can drive them, but that is where, let's say, the core challenge lies. The core challenge is how fast can you actually manipulate the gates? And that's not only true for this platform, it's true for all of the platforms, right? How fast can you manipulate the gates versus how long is your coherence time? And it's always this balance. Like if you're looking at NV centers and diamonds, it's great. You can have them at room temperature. You can set them up in a specific orientation. You leave them there and they stay for a long time because they are, let's say, encapsulated in this diamond, which is a very, very strong protection to the outside, because diamonds are very rigid material. They're very strong crystal. Now, that's nice, but it's not so easy to manipulate those and to entangle those and to run all of these gates. And that's what makes them so difficult as, for example, a platform to run quantum computers with. On the other side, you might have things like spin qubits and other materials like silicon, or you might have superconducting qubits that are operating at much, much smaller coherence times. However, you can manipulate them very fast because you can run microwave signals to actually change their spin states to couple them, to do specific gates on them. And that's where this advantage comes in. And then you have the neutral atoms and the ions that sit somewhere in between. And this is always a competition to figure out who gets the maximum out of their platform. And the maximum means how many gates can I run on the platform? Like how many qubits can I entangle? How deep algorithms can I build? So how many gates can I build until I run into this point where my decoherence is basically destroying the quantum information. That's the challenge. And that's also a challenge that, of course, will be existing for the technology that we see here that Arca is developing. And I'm, of course, excited to follow how they will actually cope with this challenge. This is about the quantum computing part, and I think it's very interesting. I would like to actually see a little bit more about the information about that here on the website. Maybe also adding some, not just a newsroom, but maybe some blog or some information on the technology side. But okay, then the other one here is on the biochip, and I will quickly go through that because it's also, of course, part of their business model, even though it might not be super relevant for the quantum technology part here. So Arca's biochip marks an inflection point in diagnostics, enabling fast, accurate, and low-cost digital testing. This breakthrough opens new applications in medical health, empowering patients and improving outcomes. So connect ion sensing biochip for at-home and point-of-care diagnostics, then precision ion sensing made simple. So our ion sensing biochip marks an inflection point in diagnostics, unlike lateral flow tests that have changed little since the 1980s. Arca's platform enables digital high-accuracy measurement previously out of reach. Integrated into disposable cartridges, it can analyze finger prick of blood in minutes, delivering the precision required for many health applications. Then you have the CKD potassium K+ monitoring, fast, accurate, and low cost. and then connected diagnostics that learn from data, so basically data-driven diagnostic. Besides that, we have a newsroom, of course. We see here the latest news is from May 19th. I'm recording this beginning of June, so it's very much up to date. And it says scaling quantum hardware with graphene. Scaling quantum hardware with graphene. Graphene is something that we talked about before, right? It's these two-dimensional lattices or crystals, whatever you want to call it, that are made out of carbon atoms. And it talks probably about how this is being used. You see here commercial viable product, the reality of graphene, and so on and so forth. So a lot of background information on this topic as well. Then we see here Archer Q2 FY26 webinar, quarterly highlight, and the road ahead. Archer Materials advances quantum and biochip platforms ahead of key 2026 prototypes, and so on and so forth. So probably very interesting to follow that one as well. As per usual, quick words about the company at the end of the video and the people that are part of the company, right? So Archer is a quantum technologies company creating solutions for global needs in computing, sensing, and healthcare, building the future of computing and diagnostics through quantum technology. At Archer, we are developing quantum technologies designed to solve high-value global challenges that conventional technology cannot. Our next-generation devices aim to advance quantum computing, sensing, and medical diagnostics, enabling breakthroughs in areas like artificial intelligence and data-driven healthcare. With strong industry partnerships and collaborations with leading research institutes, Archer is part of a global network accelerating the future of quantum innovation. Backed by a growing portfolio of granted and pending patents across North America, APAC, and Europe, we are building a foundation to commercialize scalable, high-impact quantum technologies for the world's fastest growing markets. Our goal is simple: to transform how the world computes, senses, and heals through the power of quantum technology. Then call to collaborate, then something about the team and resources here to explore more. Talking about the team, right? So here you see the board members. And of course, since this is a stock listed company, right, you have all the important, let's say, functions of the one side of the board, of course, that is required for this kind of entity. And then, of course, also an executive team. So you see a chief executive officer here, head of people, head of engineering, and then, of course, again, some way to join the team. So that's everything I wanted to say about Archer today. So from my point of view, another very interesting, let's say, technology platform that is entering the competition for building a quantum computing architecture, and possibly, and that's also something they mentioned here, right, sensors along the way, like for example magnetic sensors, I could imagine, based on what they have built, or maybe also charge sensors. So there's a lot of potential here on this technology platform, and I think it's going to be interesting to keep following on what they are doing, how things are advancing, and how basically they're advancing their own platform and how they find ways to deal with the technical hurdles that might also come along those paths. So definitely one of the interesting ones to join. From my point of view, also a very unique one. I have not seen this type of technology previously in the Hidden Quantum Champion series. However, I have already featured other technology platforms in there. And if you haven't seen those, I encourage you to go check out the Hidden Quantum Champions playlist on our YouTube channel, where you can find many other company reviews like this, which you probably like because you joined all the way until the end of today's video. With that, as always, stay hydrated and see you in the next one. Bye bye.